Hi, my name is Dave Bennett, and I'm the CTO of CacheQ Systems. I'm here today to give you a brief demo of how our tools will take your existing C program and compile it for an FPGA card. The system I'm going to use is a Linux system with a Xilinx Alveo U200 card in it, and we support a variety of different cards. You can get the full list on our website. I'm going to show you stuff on the screen, and I want to stress that what I'm showing you is actually what's going on. There's nothing going on behind the scenes. Everything that I do here you can do. You can get our software and try it yourself. I'm going to show you how to use these tools on a program that does Monte Carlo simulation of Black-Scholes. Black-Scholes is a program that's used as an algorithm that's used in the financial services sector to emulate the behavior of an options market, and it's used in program trading. And I'm not entirely sure because I'm not a financial services person, but it is representative of the kind of things that the financial services people want to do. And so we're going to take an algorithm that's written for that, and we're going to try to accelerate that on the FPGA. So first I'm going to bring up this program, bscq.c, and we're going to go through this, and I'm going to explain roughly what's going on here. At the beginning here we see this function called drand, and it takes the random number generated by the standard Linux rand function, and it converts it to a floating point number between 0 and 1. And then there's Box-Muller, and what Box-Muller does is it takes that floating point random number generator and it wants to convert that into a normal distribution, like a bell-shaped curve. And so that the input of the Box-Muller is a couple of these random numbers, and the output is a couple of numbers that will fall into that random or bell-shaped normalized distribution. BS loop, this next function here, is the guts of the algorithm. It takes two inputs, n and m, and then a vector, which is a list of the parameters. And n is the number of stocks and the size of the params. And m is the number of simulations, the number of Monte Carlo simulations you want to do. And here's the basic loop that does all of this math. Does the Box-Muller and then does math on the results to generate essentially an average range of the simulations. And then this NDF function and the function that calls it, which is check analytic. The purpose of those functions is to there is actually an analytic correct answer for the Black-Scholes, but for the purposes of the financial services, they don't want the correct answer. They want an answer that behaves somewhat like the way people in the market are going to behave, and that's the whole purpose for doing this Monte Carlo simulation. As I said, I'm not really a financial services person, so I don't know how all of that works, but that's the basic premise here. Now, if we look at main here, main is going to take the input arguments. If you don't give it any arguments, it defaults to n number of stocks is 20 and the number of simulations is 100,000. And then it allocates using malloc an array, a vector of these stocks, and then it fills in some hypothetical stock parameters that are then used by the algorithm. If you were doing this for real, you would get these data from some stock ticker, effectively, so some stock service. And then it runs the Black-Scholes. The function here, BS loop, is really the guts of the algorithm, and that I showed you that above. So this calls BS loop and then does some analysis of the results and prints out the difference between the Monte Carlo simulation and the actual analytic solution. So that's the basic algorithm here, and the first step we're going to do here is compile this with GCC. Go GCC, bscq.c, -lm because it uses the math libraries. And now we've compiled that with GCC. We'll run that and we'll get an answer. And you can see here we ran Black-Scholes over 20 options with 100,000 simulations. And we see the results of that Monte Carlo simulation, and then we can see the analytic solution. So what we see here is that this took about 1/10 of a second on my 3.7 gigahertz Core i7-8700K CPU, which is a pretty fast, reasonably modern CPU. I'm not a program trader, but the point here is that I don't have to be in order to get this code to speed up. And so the next process that we're going to do is we're going to take the same code and run it through the CacheQ compiler. So all we have to do there is type qcc bscq.c, and now we're running the CacheQ compiler, and it performs a number of steps. Now, the main process here that's going on is this is going to convert our the C program into our virtual machine model. And so we call that the CVM, for CacheQ virtual machine. And there are a bunch of benefits for the CacheQ virtual machine, and I'm going to go over some of those right now. In order to do that, I'm going to bring up our viewer. So what we see here is the CacheQ virtual machine represented as a graph. Now the graph has nodes and arcs, and the nodes are individual operations. And if I go in, zoom in here, we can see here, for example, there's a floating point multiply operation. And so the arcs are queues in the virtual machine architecture. And there are a bunch of benefits that you get by converting into the virtual machine CVM. And I'm going to go over a few of those here. The first benefit is that everything you see here that's on a same horizontal is going to run at the same time. So you get a bunch of parallelism just by converting this into this graph or representation. The second benefit that you get is that we can do pipelining on this graph. And pipelining is another form of parallelism. If you're inside of a loop, then not only everything that appears on this in the same horizontal can run at the same time, we can actually pipeline it so that everything in the vertical also runs at the same time. And you actually get a much better amount of parallelism out of pipelining than you do out of this, because you can see in this case there are a few places where it gets really wide, but there are every place that it gets really tall. So the really tall means things can be pipelined. Now, the third benefit is I can easily cut a hunk of this graph out, and that is what we call partitioning. So it's relatively easy for us to do partitioning. In this particular representation, the various pieces of code in different colors here are the separate functions, and they may or may not happen in parallel, but I can partition at any level, really. I can partition at the function level, which I'll show you later, but you could also partition at a finer grain level. And the partitioning is simply a matter of cutting a piece out of the graph and putting it into a different computational element. So the fourth benefit is that all I have to do to target a different type of computational element is come up with a way to implement these op types. Each of these nodes we call an op, and so there are a number of op types, and I just have to create a representation for those op types and for the queues, and then I can target a different computational architecture. And the fifth and final but not least benefit is memory is handled in our CVM automatically. I can access memory in one computational element, write to it in another, read it in a third, and all of that is handled automatically by when we target the architecture that falls out of the virtual machine architecture. So those are the key benefits. As I mentioned before, we can target them to different. We can target the virtual machine to different architectures, And so I'm just going to run the compiler again and talk about the various steps that we're doing. The first step we do is we convert the C code into our virtual machine architecture, That is done with two separate steps. One is we run Clang, which is a LLVM based compiler that takes your C code and converts it into the LLVM internal representation. After that, we run our program, which takes the LLVM internal representation and then converts that into our virtual machine model. Once it's in our virtual machine model, then we optimize that virtual machine model so that we insert parallelism wherever it's possible. We insert pipelining wherever it's possible. So once we have an optimized virtual machine, then we can run target different architectures. In this particular case, we are targeting a C++ implementation. And so we take the original C code, convert it to the virtual machine model, and then convert that back into C. And then once we've got C, then we compile that and generate an executable. And so to run this program, we just can run, we create, if you look here, we create a .cq file. So if you look here, there's bscq.cq. And so to run that, you have to run cq run and the file name bscq, and it will run that virtual machine model. Now we see here that it ran a little bit slower, and that let's compare this to a.out, which is our GCC version. We see that the numbers are somewhat different in this top half, and the reason why is because the GCC version is running the standard rand function from the Linux libraries, and our version runs our version of rand, which is platform independent. It works across all the platforms, FPGA and CPU and any other platforms we support. And it's also compliant with the NIST and Die Harder random number test program. So we produce we have a robust random number generator, more robust than the Linux one. So we recommend people use ours instead of the standard Linux one. But in this case, we're using the standard Linux one for the original GCC compile, and ours for our QCC compile, and that's why this top part is different. You can see the analytic result, which isn't dependent on the random number generator, is identical in both cases, and that's because it isn't doing any it isn't doing any random numbers. In general, you can expect that the GCC results and QCC results will be identical. There are instances where that's not true. There are a few cases where we do some different rounding than what in the FPGA it does different rounding than what GCC does. But in general, you should see identical results between the two. And you see here that it ran a little bit slower on the CacheQ version, but if we'd optimized both with GCC optimization, that difference would be negligible. So I'm going to copy the program to a new version so that we have the original version available. And this can all be found on the web links that are shown below the video on YouTube here. So I created a new version, and now we're going to edit that. So if you see here the call to BS loop, which as we know is where most of the action is taking place, we can see that it's bracketed with calls to this clock get time. So clock get time is going to get the system time. And for the FPGA performance simulation, we want to actually get the FPGA time that it's going to take, not the system time. So in order to do that, we have provided a function that called CQNSTime that lets you get the performance of the FPGA. Now, if you're not compiling for CacheQ, then you wouldn't want to do that. So we also, if you compile with QCC, we automatically define the CacheQ environment variable, so that or compiler or preprocessor macro, so that you can if-def code that you want specifically to run on the CacheQ mode. So we're going to call CQNSTime here. And instead of calling the clock get time. And so a bit about CQNSTime is that if we are compiling for not compiling for FPGA performance simulation, then the CQNSTime will just use the system time clock. And if you're compiling for FPGA performance simulation, you will get the FPGA time, the estimated FPGA time. So it's quite a handy tool. I recommend, personally, I always use CQNSTime instead of using the system time, because that way it just works for both. So I made these changes, and let's compile this for the normal method. QCC, we're going to compile that. So now we're going to run this. And we see that it produced a time roughly equivalent to the last time we ran it with a system timer. Shows that CQNSTime, if you're not compiling for performance simulation, will run in the same time. Now we're going to compile it for performance simulation. And in order to do that, we run QCC-T, and the -T tells it I'm interested in the timing, which is how you trigger the performance simulation. So what's happening here is it's going to again generate the CacheQ virtual machine model, and here is a GUI, memory GUI for memory pools, which I'll talk about in a different presentation. For now, I'm going to take the defaults. So it generates the CacheQ virtual machine, and then instead of targeting just a vanilla C program, it's going to target the performance simulator. And so now we have a new executable, and if I do CQ run of BS CQ_T, it's going to run the performance simulator. Now the performance simulator takes a while to run, so we're going to go away for a couple minutes and then come back. So we can see this is finished. It took about almost 4 minutes to run the simulation, but the result we got here, now we can see what the FPGA time would be, and it's about 4 milliseconds. And that compared to about 100 milliseconds, a little over 100 milliseconds for the GCC run. So we are at this point about 25 times faster. Now again, we could go to FPGA right now and we should see about a 25x improvement. But I know this code a little bit, and I know that there's one really simple optimization I can do. So I'm going to do that optimization right now, and we'll see the results of that before we go to FPGA. So we're going to call this BSCQ_4.c. Again, you can have all of the copies of this code from the links below. And we're going to do another little trick that our tool provides, and that is inside this loop, which I know from the code that this loop is where all of the time takes. Now, we do have a capability to do profiling, and that I will show you in another session. But in this session, I know that this is the loop I want to do, so I'm going to insert this function, which causes it to run multiple copies of this loop in parallel. I have a pseudo function _CQ_unroll, and this is documented in our documentation for the tools. And I'm going to tell it to unroll this loop 4 times, and then it will run 4 copies of this loop in parallel, which should give us approximately a 4x speed up over the 25x we already have. So I'm going to compile this here with the timing again. And it's going to, again, give me this memory, and I'm just going to accept the defaults, and then we are going to generate timing, a performance simulation executable, and I'm going to run that with CacheQ run. And again, this is going to take a couple of minutes, so we're going to take a break and be right back. So what we can see here now is that this is finished, and it took about 3 minutes, which it actually ran faster because the resulting performance simulation actually ran faster. It ran about 4 times faster as we expected. And so now we're at 1 millisecond, whereas the x86 was at 100 milliseconds. So now this is about 100 times faster. Now we could unroll more depending on the size of the FPGA that we're targeting, but we're going to go with this result. One of the things worth noting is that this unroll, we are working on a tool that will do that automatically based upon the size of the loop that it's unrolling and the size of the device that you're targeting. That should be available sometime around the beginning of 2020. So for now, though, the next thing we want to do is we actually target the FPGA. So now we're going to talk about partitioning. We're going to want to run some of the code on the FPGA and some of the code on the CPU. Now, the simplest thing to do is just to let the tool decide how to do that, and we recommend that. But in the interest of this demonstration, I'm going to show you how you could influence the partitioning manually. And so in order to do that, we're going to run, once again, this is based on QCC. This time we're going to run the -TP flag. So but before we do that, I want to show you, if we do QCC-H, we show you a list of options. And we look at the -TP flag here, and you see that there are certain target platforms we support. And one of those, and the one that is in the machine that we're using, is the Xilinx Alveo 200 card. And so we're going to need to target the Alveo 200, so we want to use LX200 on the command line. Once again, we use QCC, and we do -TP LX200 because we're targeting that card. And then we want to say yes, which causes the GUI to come up. And then we want to do that in BSCQ_4, which is our unrolled by 4 version of the program. So there we go, and now it's running. And now it's running the pools again. We're going to accept the default there, and now it's going to bring up the partitioning GUI. Now, the partitioning GUI, you'll see 3 columns here. The first is unassigned, the second is Linux Edge, and the third is VU9P. So anything that's unassigned will get partitioned automatically by the pool. Anything moved on the edge means it will run on the CPU, and anything in the VU9P means it will run in the FPGA. So for our purposes, we kind of know the main wants to run on the edge. The main, remember, allocates the memory, initializes that memory, and then calls BS loop. So we're going to want BS loop to run on the FPGA, and we're going to let the tool decide what to do with the rest. And the tool looks at the connectivity and decides what makes sense where. You might be tempted to just manually partition all of it, but we don't recommend that because a lot of times you will find different effects than what you really expected by doing that, because some things you thought were only used on the edge turned out not to be only used on the edge, and vice versa. So we're just going to let the tool do the rest. We're going to put main on the edge and BS loop and the FPGA and let the tool worry about the rest. And so we save that, and now the tool is doing the partition. And right here it executed PRT, and then it executed PRT, and then, which is the partitioner, and then it generated some data. And the key piece of information here is the number of crossing FIFOs. If you remember when we showed the CVM graph, you saw the lines which were represented Qs. Well, those got converted into FIFOs for the FPGA, and the crossing FIFOs is the number of times an Q went across from the CPU to the FPGA, and there are 24 of those. So the partitioner is done, and it has produced a result which we can then target to the FPGA. Now, if you're using the Xilinx tools and you're familiar with the Xilinx tools, that if you do look here, there are some system Verilog files, and you can take those system Verilog files and target the FPGA. We have scripts that do that automatically for you with the Xilinx tools. But the Xilinx tools are somewhat challenging if you're not familiar with them. So to help you with that, we have an arrangement with a company named Plunify. And Plunify will run the Xilinx tools in the cloud for you. And for the Plunify flow, we basically issue the same command and we add -f Plunify. And when we do that, we're going to get the same GUIs. So I'm going to quickly zip through these. And there we go. And now if we look, it is executing Plunify, and that will take a few seconds here, and then we're done. And now it's generating the CPP, which is going to run on the host only. The bitstream will run on the FPGA. So Plunify is going to send us an email, and it has not yet arrived. So we're going to wait a minute, and then as soon as the email comes, we'll come back. Okay, so we've gotten this email from Plunify telling us that our job has started, and it will take several hours to complete this job. So I'm actually going to show you what would happen, the email that you would get when the job finishes. So this is the email of a previously started job, the same job, and so we would get this email saying that the job is finished. Now I can also query this job by running CQ run -p, and that would query the status, but in this case I'm using the job that I previously started, and so we will get, in this case, if the job is completed, the -p actually downloads the results of the job and stores that in the CQ file. So we're going to do that right now, and with this we'll download the finished bitstream from Plunify. And it's checking the status, it's complete, and now it's downloading the bit file, and then it downloads some other items here. So we completed the job, we've placed and routed, and we are actually ready to try to run this. But before we do, we have to program the bitstream into the FPGA. So that we do CQ run -b to program the bitstream, and we're going to do that, and this takes about 30 seconds, so we're going to actually pause for a moment in the video. Okay, it's finished programming the bitstream, so now we're actually ready to run this. So to do that, we do CQ run CQ_4, and now it's actually going to run that on the FPGA. And we see here it completed in about 1.5 milliseconds, which is a little slower than our simulation said it would be. And that's because there's a little bit of startup time when you run it on the FPGA. So to give you the real feel for how much difference there is, we're going to run this on the with 10,000 stocks. And first I'm going to run it on the x86, and I'm not going to actually speed this up. So if you don't want to wait, you can jump ahead about 40 seconds because this is going to take a while to run. We're going to sit here and watch this run on the x86 so you can get really the flavor for how much better it is when we run this on the FPGA. So it's going to take about 50 seconds to run this. I think we're probably about halfway through. Anyway, If you are interested in trying out our tools after you see this demo, you should go to our website, www.CacheQ.com, and you can sign up for a trial. So it finished on the x86, and now we're going to run it on the FPGA, and you will see 10,000 stocks, and you'll see the difference. There it is. That just ran 10,000 stocks on the FPGA. It took a little more than half a second, which is roughly 100 times faster than it took on the CPU, which is exactly what our simulation told us it would be. So again, that's the demo. If you want, follow links down below, and you can sign up for our tools. Thank you again, and we'll be seeing you.